Electron configurations, that'll be the topic of this lesson. And in the last lesson, we learned that Bohr kind of thought that electrons went in a circular orbit around the nucleus. But in this lesson, we'll learn that electrons really live in these orbitals, which are kind of three-dimensional regions of space around the nucleus instead. And we're going to learn that the electron configuration is really a description of where all the different electrons in an atom actually live. Now, this lesson is a part of my high school chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year. So if you don't want to miss one, subscribe to the channel, click the bell notification. You'll be notified every time I post a new lesson. Okay, so it turns out we got to have a little discussion of what the atomic orbitals look like, and I'll put them up on your screen here somewhere. But your atomic orbitals, instead of these circular orbits again that Bohr thought existed, these atomic orbitals are actually three-dimensional regions of space. And it turns out the three common types you got to understand are s orbitals, p orbitals, d orbitals. I said three types, four types, and f orbitals. And it turns out there's not only four types. It turns out you can actually go on to g orbitals and h orbitals that you'll never hear probably anybody ever mention or even allude to outside of the allusion I just made. But they do exist. We just don't have any elements that actually use them in what we call the ground state. But we do know they exist, and we have good evidence for it, but we're not going to talk about them in this class at all, and you're probably not going to talk about them in any college course you might take in the future either. But you do have to kind of know something about s orbitals, p orbitals, d orbitals, and f orbitals, and that includes kind of knowing what the sps and ds actually look like. Now, the f orbitals are actually pretty complicated, pretty complex three-dimensional shapes, and you're probably never even going to see a picture of them. You can look them up online if you need to, but the s orbitals, the p orbitals, d orbitals, you should know what those look like. Now, it turns out there's a single s orbital in what we call different shells. So, and these s orbitals are spherical in shape, and they're solid like a bowling ball, not hollow like a basketball. So they're solid. An electron can live anywhere from the nucleus out to the outermost boundaries of that s orbital, if you will. It is a solid sphere, not a hollow sphere, where you'll find that electron. Now, it turns out that any orbital in the universe can hold exactly a maximum of 2 electrons. So that's the deal. And it turns out these 2 electrons have to have an opposite, what we call spin. And we often represent those using arrows, one pointing up and one pointing down to kind of represent this opposite spin. Now, what spin actually is beyond the scope of this course. And the truth is, we don't kind of exactly know what it is. We kind of know a little bit about how it behaves, but we don't really know what spin is either. Somebody kind of misnamed it back in the day, and that's, like I said, it's again beyond the scope of this class. But keep in mind, we'll just represent it though with kind of these opposites. And just like charge has 2 opposites, and we call them plus and minus, spin has 2 opposites as well, and we'll call it spin up and spin down, and we'll just represent them with arrows pointing in opposite directions. Now, it turns out that every orbital in the universe that you're ever going to see presented in this class, or likely any other chemistry class, can hold a maximum of exactly 2 electrons, but they have to have opposite spins, one spin up and one spin down. And that's just the way it works. That's something to file away and memorize in your head. Now, this diagram that we're going to use here a little bit, every box on here is going to represent an orbital. So, and we're going to be able to put arrows in here, one up and one down. And it doesn't really matter what order we fill them in versus up or down. But if I'm going to put a maximum of 2 electrons in an orbital, one has to point up and one has to point down to correspond to those spins. All right, so the s orbital again is spherical. So when you move up to the p orbital, so there are 3 p orbitals, it turns out, and they are dumbbell shaped, we say. And we have one that lies on the x-axis, one that lies on the y-axis, and then one that would lie on the z-axis. And that's the difference between those. Once you go up to d orbitals, there are 5 of those. And 4 out of the 5 look like a 4-leaf clover. What's different is their orientation in space. And some are on the XY plane, some are in the YZ plane, some are in the XZ plane, some are on the axes, some are in between the axes. So, but then there's one funky one, which has 2 lobes, one above and one below, right on the Z-axis, and then this kind of like inner tube around its waist, if you will, of electron density. And you should recognize that shape as belonging to one of the d orbitals. So notice this is interesting. There's 1 s orbital, 3 p orbitals, 5 d orbitals, and when we get to f's, there'll be 7 f orbitals. They just count on the odd numbers, which is worth noting, and that's kind of what we see here. If we look in the first shell, we'll find out that the only thing that exists is an s orbital. In the second shell, so of electrons, there's going to be s and p. In the third shell, s, p, and d. In the fourth shell, s, p, d, and f. And so now we got to talk about this idea of shells of electrons. Because in Bohr's model, he just had orbits. He had orbit 1, orbit 2, orbit 3. Well, it turns out those orbits were actually shells of electrons that might contain one or more orbitals. Like that first orbit, it turns out only had a single orbital, and it was an s orbital that was spherical in shape. But the n equals 2 orbit that Bohr corresponded to actually was composed of 4 different orbitals, a single s and then 3 p orbitals. And so, these 4 orbitals comprise an entire second shell of electrons, we say. And that shell we might break up into subshells. We might talk about the s subshell and the p subshell. So a little more terminology here. Notice the third shell, you now have 3 subshells in the third shell. You have the s subshell, the p subshell, the d subshell. In the fourth shell, you have 4 subshells, the s subshell, the p subshell, the d subshell, and now the f subshell. So every time you go up, so it turns out this is increasing energy as we go up, but every time you go up in energy to a new shell, you get a new type of subshell. So if we diagrammed it up here, the 5th subshell would have S, P, D, F, and G, which again, we're never going to study. So we run out of stable elements by the time we ever get to anything with that many of electrons. And so there are no stable elements that actually put electrons in the G orbitals in what we call the ground state. So we'll get there. All right, so every box on here represents an orbital, and every orbital in the universe can hold 2 electrons. And we want to look and say, okay, well, how do we figure out where the electrons in an atom are actually existing and stuff like this, and these s orbitals, these p orbitals, there's d orbitals, and we have a set of rules for figuring these out. So, and the first rule is going to be what's called the Aufbau Principle, and it says when you're filling in the electrons in an atom, always fill them into the lowest energy spot first. So we've got increasing energy going this way, going up. And so Aufbau would say, well, if you got 1 electron, make sure you put it in the 1s orbital. So we'll put it in the 1s orbital, and I'll make it spin up. I could have just as likely have made it spin down. It is arbitrary. So then Mr. Aufbau says, okay, if you got another electron, well, then put it in your lowest energy empty position, your lowest energy opening, if you will. And that I still got another opening right there. Every one of these boxes represents an orbital, and every one of them can hold a maximum of 2 electrons. And so the next one would be a spin down. And again, it didn't actually matter which one of these I filled in first. It could have gone either way. And so this is, if something has 2 electrons in what we call the ground state, the lowest energy state, those 2 electrons would be in a 1s orbital. So let's take a look at this for a second. So if we take a look at hydrogen, hydrogen here is atomic number 1. And being atomic number 1, so for this purpose, we're going to only discuss neutral atoms. And for neutral atoms, they have an equal number of protons and electrons. And that number would be represented by its atomic number. So hydrogen with an atomic number of 1, as long as we're talking about neutral hydrogen, not hydrogen ions, we're going to be talking about a 1 electron system. And for a 1 electron system, that 1 electron is going to be in a 1s orbital. And to represent that, we would write 1s1. There's a single electron in the s orbital of shell number 1. That's kind of the way we read that. So 1s1, and we refer to that actually as its electron configuration. That's for 1 electron. Now if we move on to helium here, so helium is atomic number 2, so he's going to have 2 electrons, and like we said, if we fill in that second electron, it goes also in that 1s orbital. And so for helium, we'd give it what we call electron configuration by saying 1s2. We have 2 electrons in the 1s orbital. Cool, that's the electron configuration. And we just keep working our way up. The Aufbau principle says, go, if you got 3 electrons, third one's going to go in the next highest energy orbital, which would be the 2s. And again, it doesn't matter if you start with spin up or spin down. So this one I'll start with spin down. It is arbitrary. So, and if we want to write this out, well, who's got 3 electrons as a neutral atom? Well, that's atomic number 3, and that's lithium right here. And so we would say 1s2, 2s1. And again, that would mean that we have 2 electrons in the 1s orbital. And then we have 1 electron in the 2s orbital. And that's lithium's electron configuration in the ground state. So moving on down the chain, we'll move over to beryllium here. And beryllium's atomic number 4. And if we have a 4th electron, next available opening, next lowest energy available opening, is also in the 2s. And so beryllium here, 1s2, 2s2. And that is beryllium's electron configuration. Well, let's keep going up the chain here. So Next highest energy orbital would be the 2p, and it could be any one of these three. So it turns out this is our first example of coming across equal energy orbitals. So these are all at the same vertical level, if you will, because they're all the same energy. And when they're all the same energy, we have a word for that in chemistry, and it is degenerate. So same word your mom might use for one of your ex-boyfriends or something like that, degenerate. So, but degenerate in chemistry terms and physics terms means equal energy. And so these p orbitals are degenerate orbitals. And when that's the case, it doesn't really matter which one you put the electron in first. So I could put it in the one on the left, the one in the middle, and the one on the right. It's arbitrary, it doesn't matter. However, because in this country we happen to read left to right, we're probably going to stick it here just out of habit. If you came from a country where you read right to left, then you'd probably stick it here out of habit instead. But you could stick it in the middle first. It doesn't matter at all. And so I'm just going to stick it on the left where I would normally stick it, and I made it up, which is just my habit. But again, I could have put it up or down in any one of these three orbitals. It would not make a difference. Now that's going to be boron, atomic number 5. And that's going to be 1s2, 2s2, and now 2p1. Cool, and that's boron's electron configuration. Let's get a better looking B out of that. That just looks terrible. So B for boron. So that's atomic number 5. We'll move on to atomic number 6 here, carbon. So we're on our way to, 118 elements. We're just going to do 118 of these, right? No. We'll stop here in a little bit, but we'll definitely get to some more complicated examples as well. But we'll move on to carbon here, atomic number 6. So, and in this case, we got one more electron. And so now we need a rule. So it turns out, where do I put that next electron? Because I could pair it up here, or stick it here, or stick it here. They're all equal energy. So how do we decide? Well, it turns out these electrons are negatively charged, and they repel each other. And so if you have a choice, because you have equal energy orbits, make sure every one of those orbitals, I should really say, every one of those orbitals gets 1 before you pair any of them up. To put 2 of them in the same orbital when they repel each other would be a higher energy state. And our goal is to make the lowest energy possible configuration. And so in this case, that's Hund's rule. Hund's rule says when you have degenerate orbitals, make sure that every orbital gets 1 before any orbital gets 2. It's kind of like you have a 3-bedroom apartment, and you have 3 guys living there. And if 3 guys are living there, then each guy gets their own room. But once you get a 4th roommate in there, now somebody's going to have to share. That's kind of the way this works as well. So every one of these orbitals that are equal energy get 1 electron before we ever pair any of them up. And so in this case, whether I stick this 6th electron in the middle orbital or the right orbital, it does not matter. Although one other thing does matter, is that when you have these what we call unpaired electrons, they have to point the same direction, have the same spin, we say, either both up or both down. Now, I made them both up. We could have just as likely have made them both down. And it turns out when their spins match, that actually lowers the energy of the configuration as well. And again, our goal is here to get the lowest energy configuration possible that we call the ground state electron configuration. Okay, so this is what carbon looks like. And if we draw out the written form here, we'll get 1s2, 2s2, 2p2. Cool, and we could just keep working our way up through this. So carbon ends with 2p2, nitrogen, we add another electron, it would end, same thing, but would end with 2p3. Oxygen, same thing, but with 2p4. Fluorine, 2p5, neon, 2p6. And so it turns out we can actually use the periodic table to kind of make some patterns evident. And so it turns out that once you got through 2p6, this would be full, and then you'd move on your way to 3s. And once it's full, you'd move on your way to 3p and do the same kind of thing. So, but after 3p, it turns out you look at 3d and 4s, and they're really close in energy, but it turns out this 4s is just a little bit lower than this 3d, so you'd actually fill in the 4s's before the 3Ds. And you need to remember this. Now, there's a couple different ways you can remember it, and my favorite way is just to memorize it based on looking at the periodic table. So it turns out that every time we go up in atomic number, we're adding another electron, and we can think of each element as representing that one additional electron it picked up. So like carbon here picked up one more electron in that second position in the 2p orbital there, so 2p2. And we can kind of think of that one electron, or as carbon is representing that one electron on the periodic table. And so 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. And then we move on to level 3. 3s1, 3s2, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. And then the 3p's would be full. And then we'd start back over, finishing up argon. We move on now to potassium in atomic number, and that would be 4s1, 4s2, corresponding to those two electrons. Then we move over to the 3ds, and it would be 3d1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So to speak. We'll find out a couple exceptions in there, but that's generally the way this works. Well, it turns out we can kind of just look at the periodic table to figure some things out. Now, it turns out, and I got a copy of this on your study guide, and I'll put one on the screen here, so that this is what we call the S block over here. These first two groups on the periodic table, that's the S block, because they're going to represent the electrons in the S orbital. In the S subshell of any level here, there's only one orbital, so you can only hold 2 electrons, and that's why there's only 2 columns. Now, it turns out this section right over here we call the P block right here. So in that P block, there are 1, 2, 3, 4, 5, 6 columns, and those 6 columns represent the 6 electrons that can be held in the P orbitals. There are 3 P orbitals that can hold 2 electrons each for a grand total of 6 electrons, hence 6 columns. And it'd be P1, P2, P3, P4, P5, P6. So which would what you see at the end of the electron configuration. So if I gave you fluorine, you'd know it would end with row 2, 5th one over in the P's, 1, 2, 3, 4, 5, so it should end with 2p5. Chlorine would end with 3p5. Bromine would end with 4p5. Iodine would end with 5p5. So astatine would end with 6p5. That's the way this works. So as far as what it ends with and stuff like this, and you would just then fill in everything up until that point. So we have the S block, we have the P block, and now we have the D block. Now the D block are the transition elements right in the middle here, these transition metals, and there are 10 columns, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, corresponding to the fact that there's 5 d orbitals that can hold a total of 10 electrons. So that's what that matches up with. And then finally, you've got the F orbitals over here. There are 7 of them. Don't forget there's 1s, 3p, 5d, 7f. They count on the odd numbers. So 7 F orbitals, and 7 F orbitals could hold a total of 14 electrons, and that corresponds to the lanthanides and actinides down here. That's the F block. And notice there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 columns there, corresponding to the 14 electrons you can fit into the F subshell. Cool. So this is the way this works. One thing you should note, so when you look at the S orbitals like hydrogen, well, helium really would belong here by this convention. So this still corresponds to the 1s, even though it's over here. But again, the key is that the periodic table is designed by things of similar reactivities, and helium reacts just like the rest of the noble gases in being that it doesn't react with much of anything, or anything in helium's case. So that's why it's kind of arranged this way. But in terms of electron configurations, helium would really belong over here in the S block. So, but hydrogen and helium represent the 1s electrons, lithium and beryllium the 2s, sodium, magnesium 3s, potassium, calcium 4s, rubidium and strontium 5s, 6s, 7s. That's the way that works. Same thing here with the P's. Notice there are no P's in the first shell, and that's why there's no row of elements right here. But in the second period, we have a row of P elements to correspond to the 2p subshell. And so boron through neon would be the 2p. So aluminum through argon 3p, gallium through krypton 4p, indium through xenon 5p, thallium through radon 6p, so on and so forth. Now, one thing you need to understand is that the D block and the F block don't correspond to the row that they're in. They're always a little bit behind. The D's are always one row behind. So in this case, we've got potassium and calcium that represent the 4s electrons, gallium through krypton represent the 4p electrons, but scandium through zinc represent the 3d. They're always one row behind. So from scandium to zinc is the 3ds, from yttrium to cadmium is the 4ds, and then from lanthanum to mercury is the 5d electrons. That's the way that works. The F's are actually 2 rows behind. So these F blocks, if you notice, the periodic table should really be a lot wider so that we could actually stick the F's right here between the S block and the D block. And there's a little bit of funkiness that goes on right there that we're not going to concern ourselves with. But in this case, so your F's, these are the 4F's and the 5F's. And notice they're 2 rows behind because 58 would come right in this row. That's the 6. Notice it's row 6, 6s. Then you'd get the 4f. Then you'd go back to the 5d. So, and then back up to the 6p. And so they're 2 rows behind. We're in row number 6. And the f's that would be in that row are the 4f's, 2 behind. The d's that are in that row are the 5d's, 1 row behind. And that's the way this works. And so if you're given, any random element, you can just read it off the periodic table and just fill in all the electrons till you get there. So for example, we kind of went in order, working our way up one by one by one, but that's going to be a huge pain in the butt. So let's just say we choose bromine. And we want the electron configuration of bromine here. Okay. Well, in this case, I could tell you already what it's going to end with. It is in the P block, and it is in the 1, 2, 3, 4, 5th column over. So it's going to end with P5, and it's in the 1, 2, 3, 4th row down, and so it's going to end with 4p5. Now that's what it ends with, though. We got to fill in everything all the way up until that point. Well, we always start with 1s, which is what hydrogen and helium represent, and so that's 1s2, and then lithium and beryllium represent the 2s electrons, so that's 2s2. And notice we say 1s2 and 2s2, not 1s squared and 2s squared. It's 1s2, 2s2, that's the way we say it. So after lithium and beryllium, we go boron through neon is the 2p's, and that's 2p6. We're going to fill them all up, 2p1, 2, 3, 4, 5, 6. And then we'll move on to sodium and magnesium, which is the 3s. Back in the s block again, so 3s2. Move on from aluminum through argon, it'll be p1, 2, 3, 4, 5, 6, so 3p6. So after argon, we'll move over to potassium, and potassium and calcium represent the 4s electrons. So that's going to be 4s2. And then finally scandium through zinc, going back to the D block now, but 1 row behind. So it's not the 4d, it's the 3d electrons, but it's all 10 of them. Cool, and then finally, now we're going to get to bromine and the 4p's. But it's not, we're not going to fill them up. We're only going to get 1, 2, 3, 4, 5 electrons in the 4p's. And like we said from the get-go, it was going to end with 4p5. Cool, that's the electron configuration for bromine. Notice if I asked you to come to the board here, one, obviously, through the camera, that's a little bit challenging. So, but if I said, hey, come and give me the electron configuration for uranium, well, that's going to suck. I mean, if bromine went over half my board, uranium would take more than 1 line on the board. It would be a huge pain in the butt. Point is this, though, is that we have a shortcut. We have what's called an abbreviated electron configuration. We call it the noble gas configuration. And the way it works, it says, this would get really tedious for these big ones down here. So you know what? Let's just shorten it up. The last noble gas you cross on the way to your element, make a note of that. So with bromine, the last noble gas we crossed on our way, starting from hydrogen all the way through, we crossed helium, then we crossed neon, then we crossed argon, and we never made it to krypton. So the last one we crossed, though, was argon. And that represents everything you see in that box right there. And so what they say is instead of writing all this out, just use brackets and write argon. And that represents 1s2, 2s2, 2p6, 3s2, 3p6. It represents all of this. And then just write what's left. And so argon, 4s2, 3d10, 4p5, and that's what we call the noble gas configuration, this abbreviated electron configuration. So both of these are correct. This is the longhand standard electron configuration. This is the noble gas abbreviated configuration. You are probably on the hook for knowing both of these and knowing how to come up with both of them. But again, for the big elements, noble gas configuration is much to be preferred. All right, so needed a little room here. So we've learned kind of how to do standard electron configurations as well as noble gas configurations. And what's nice is we can do it by looking at the periodic table, which is great because you're always going to have access to a periodic table. They're typically stapled on the back of the exam. They're up on the walls of the rooms. So you can find them on credit cards, on ties, the inside cover of your textbook. They're online everywhere, right? I've seen them on tattoos. I mean, they're everywhere. Periodic tables everywhere. You're always going to have access to one, and so learning how to do electron configurations based on the periodic table is super handy. It's not the only way to learn and remember how the order goes and stuff like that. It's just my favorite because you will always have an electron configuration, and it requires less memorization on your part. So that's where we're going to go with it. And we've now learned how to do standard ground state electron configurations, but there are 5 notable exceptions. Now, it turns out there's actually way more than 5 exceptions, but there's 5 notable ones that you're potentially on the hook for. And it turns out those are chromium and molybdenum here, and then copper, silver, and gold here. And we'll see why they're in the same group here, the same column on purpose. And we're going to start with copper here. And so if we take a look at copper, and let's just do the noble gas configuration. Last noble gas before copper is also argon. And if we didn't know this was an exception, this is what we'd come up with. We'd have argon, and then we'd have potassium and calcium represent 4s2. Scandium to copper would be 1, 2, 3, 4, 5, 6, 7, 8, 9. And so you'd have 3d9. And it turns out this is not the ground state electron configuration for copper. So it turns out copper being an exception doesn't follow the normal rules. If you were asked for the ground state electron configuration of copper and you said this, you would be wrong. So it turns out that copper knows something that we don't. So it turns out if you have a completely filled subshell, that makes things a little lower energy, a little more stable. Or if you have an exactly half-filled subshell, that gives you all those unpaired electrons lining up in the same spin, which also lowers the energy and makes it more stable. And so the goal here is that we'll figure out that copper is an exception because we're going to maximize the number of either filled or half-filled subshells. And we'll do that by stealing one of the electrons from the 4s and putting it up into the 3d. And so it turns out the correct electron configuration for copper is 4s1, 3d10. As 4s2, 3d9, the s subshell was full, and that's good. That's stable. But 3d9, it's not full because it's not 10, and it's not half full because it's not 5, and there's nothing particularly stable about that. But notice what happened when we stole one. 4s1, 3d10. With s1, the s's can hold 2, that's exactly half full, and that's good. And then D10, that's completely full, and that's good. And now both subshells are in a good low energy place, and that's what makes this the more stable configuration, it turns out. So this is an exception, right? You know, following the normal rules of Aufbau Principle and Hund's rule and stuff is not going to lead you here. It's one you need to memorize. So copper's ground state electron configuration is argon 4s1 3d10. And it turns out silver and gold do the same thing. So silver is going to end, instead of ending with 4s1 3d10, would end with 5s1 4d10. And gold, same thing, one row further down. Now it turns out that, again, chromium and molybdenum do the same thing. And again, if we take a look at chromium and follow the normal rules, not realizing it's an exception, we'd come up with argon, 4s2 for potassium, calcium, and then 3d, 1, 2, 3, 4 to chromium. And again, this is not the electron configuration in the ground state for chromium. Totally, this is wrong. It's an exception. If we just follow the normal rules, we'd go here. It's not right. So in this case, chromium does the same thing copper does. He's going to steal one from the s and put it into the d. And the actual ground state electron configuration for chromium then is 4s1, 3d5. And you can see why we do this. So the wrong one had a filled s, and that was good, but the d wasn't full or half full. It wasn't 5 or 10, and nothing special about that. But now the s is exactly half full, and the d is exactly half full. They're both subshells, in this case, are in good places, in low energy places. And that's why this is the more stable electron configuration here. Cool. And again, molybdenum would do the same thing one row further down. Molybdenum, instead of being, ending with 4s1 3d5, would end with 5s1 4d5, way it works. Now, it turns out tungsten doesn't do this, and I don't know why and don't care to, you know, don't care to address it because it's not something you need to know, but these are the 5 exceptions you are on the hook for. Again, copper, silver, gold, chromium, molybdenum. There are other exceptions, like platinum down here is an exception, but not one we have like an easy way to explain the rule for or anything like that, and not one you're on the hook for. Now, again, if you've got, you know, some sort of homework question where you've got access to the internet and stuff like that, they could ask you about platinum, but on the test, they can't ask you about platinum because it's an exception and not one we're going to require you to memorize. So, but these 5 you are potentially on the hook for, and oftentimes though in high school, your teachers might even leave these 5 out, just FYI. All right, so now that we've looked at standard ground state electron configurations, and we've looked at the 5 exceptions you're on the hook for, now instead of neutral atoms, we've also got to talk about ions. Ions either having a negative charge, which we call anions, or a positive charge, which we call cations. So let's go back to bromine for a second. So most common ion that bromine forms is -1, and we learned back in the day that bromine being a halogen likes to be -1 so that it looks like a noble gas, i.e. has the same number of electrons as a noble gas. And so in this case, with a negative charge, that means you're gaining an extra negatively charged electron. And so if bromine looks like this, argon 4s2, 3d10, 4p5, just if it's -1, add 1 more electron. Had it been -2, we'd add 2 more electrons. Had it been -3, we'd add 3 more electrons. So in this case, I just got to add 1 more electron. And so that's going to get me to argon 4s2, 3d10. And instead of 4p5, I've got that 6th electron I can stick in there. Cool. Notice also, though, we could have just simply written this as krypton. That is the same as a noble gas, and technically either one of these would be correct. So as the ground state electron configuration here for Br-, the bromide ion. So anions aren't so bad. Add electrons. Well, it turns out cations are similar. Like let's say we got sodium. So sodium is right here. We'll go with the noble gas configuration. The last noble gas we cross before sodium is neon. And then it's just simply 1 more electron, so 3s1. And that's sodium. And the most common ion sodium forms is a +1 ion. And when you've got a positive ion, you need to remove electrons. +1, remove 1 electron. +2, remove 2 electrons, so on and so forth. And so in this case, we're simply just going to have neon. We're going to remove that highest energy electron, that 3s electron, and just simply be left with neon. And that's what sodium +1 is. Cool. Now this all seems great until you get to these transition elements. And then you've got to remember something else. And it's a real big pain in the butt. So let's say we've got iron for a second. So an iron, last noble gas is argon that you cross to get to iron. Iron's right in the middle of the 3Ds there. And then it's going to be 4s2 and 3d1, 2, 3, 4, 5, 6. So argon, 4s2, 3d6. So what if we have Fe2+ or Fe3+, both of which are pretty common? We got to remove 2 electrons for Fe2+ or 3 electrons for Fe3+. Well, if I remove 2 electrons, we'd be inclined to be like, well, just remove 2 of those. That's not the way it works, it turns out. So with the transition elements, and technically it works this way with the lanthanides and actinides as well, if you ever see those, but with the transition elements, you have to remember that you remove from the highest shell number first. And so in this case, what's a higher shell number? Shell number 4 or shell number 3? Well, shell number 4 is a higher number. And so when you go to make a cation with the transition elements, you got to remember like, oh, I'm going to pull out the 4 S's before I remove any 3Ds. And so for Fe2+, it's the 2 4s electrons that get removed. And so we're just going to say argon, and you don't even write it. It's empty. If it's empty, you don't write 4s0. You just leave it out and write 3d6. And so the electron configuration for Fe2+ is argon 3d6. Now, if we'd had Fe3+, we'd have to remove 1 more electron, and it would have been argon 3d5. Once the S's are empty, then you got to start tapping into those Ds. But for the transition elements, you got to remember, remove the highest shell number first. So is the way it works. Now, there's a very complicated reason for why this happens that I'm not going to get into. So it's not super important as far as the reasoning goes. But the fact that this is the way you remove electrons for a transition metal cation, that you definitely need to know. Okay, so now we've got to talk about what's called the valence electrons. And so it turns out we give we put two different labels on the electrons in an atom. We look at the outermost shell and we call those the valence electrons, and then everything closer to the nucleus than those we call the core electrons. And the reason we kind of get this delineation between the two is because it's the valence electrons that are involved in making and breaking bonds. That's why we make a point of giving them a special name. And so you want to be able to look at a particular electron configuration or an element or something like that and be able to tell how many valence electrons it has. Now, I'm going to give you the easy way first, and then we're going to kind of go work our way back. So it turns out for the main group elements, so group 1, 2, and then the P block over here as well, it turns out you can just kind of look at them and know exactly how many valence electrons they are based on where they are on the periodic table. So the alkali metals have 1 valence electron. The alkaline earth metals have 2 valence electrons. Borons column 3 valence electrons. Carbon 4. Nitrogens column 5 valence electrons. Oxygens column 6. The halogens 7. And the noble gases 8 valence electrons. And for those, that's great. So if I said, how many valence electrons does bromine have? You'd be like, 7. He's a halogen. 1, 2, 3, 4, 5, 6, 7. And that's the way it works. In fact, notice fluorine, chlorine, bromine, iodine all have 7 valence electrons. Oxygen, sulfur, selenium, tellurium all have 6 valence electrons. That's the way it works. You can tell just by looking on here. But the moment I ask you about one of these transition metals, that's when things are going to get a little bit tricky. So let's go back and take a look at some of these trick examples and how we figure out how many valence electrons something has. So, and let's start with sodium here. So sodium, typically, as long as you're one of the main group elements, everything past your last noble gas is valence. And so in this case, that 3s1 is the 1 valence electron that sodium has. And again, all the alkali metals have 1 valence electron. Cool. Everything that neon represents, which is everything from 1s2, 2s2, and 2p6, those are the core electrons. All right, if we work our way to bromine up here, so we can see that we've got argon 4s2, 3d10, 4p5. Now we know bromine's got 7 valence electrons based on its position, which is where things get tricky because that means that these 2 and these 5 are considered the valence electrons, but the 10d electrons, even that are past the noble gas configuration, are not considered valence electrons. Okay, so we might try to come up with a rule that says, well, the Ds don't count as valence, but sometimes they do. Okay, well, let's go look at iron for a second. So we'll look at this one right in the middle that we set up, not the Fe2+, but the Fe. And it turns out we would consider iron here as having 8 valence electrons, which means you have to count the 2s electrons and the 6d electrons. And that's where things get complicated. So here the d electrons count as valence for iron, but for bromine they don't. And so here's the deal. If your d electrons are full, well, that's part of the 3rd shell. We already filled that up. They don't count as valence anymore. We're in the 4th shell now. So once they're full, they're considered part of the previous shell, not the valence shell. They're considered part of the core electrons, and that's why they don't count here. But here, those d electrons, they're not full. They're still part of what we'd be filling up, if you will, and so we count them as valence. And that's why you're still going to count the 4 s's and the 3ds since they're only partially full, and we'd still be in the process of filling them in, so to speak. And so if you have d1, 2, 3, 4, 5, 6, 7, 8, or 9, they count as valence. But once you get d10, they don't count as valence electrons. Cool. And you might be asked a question that simply says, identify how many valence electrons something has. And again, as long as it's one of the main group elements, you can just tell based on where it is in the periodic table. But if I ask about one of these transition metals, that's where it could get a little bit tricky, and now you know how to address that. All right, so let's say I told you that I had an iron atom in my back pocket. And this iron atom looks like this. Am I telling the truth or am I a liar? So, well, it turns out I'm telling the truth. Well, actually, I'm lying because I don't have an iron atom in my back pocket. But it is possible that an iron atom could look like this because it's in my back pocket, it's excited. So we call this the excited state. So all the rules we've learned, the Aufbau Principle and Hund's rule and stuff, this all corresponds to the ground state electron configuration, the lowest energy state. But we also learned in the last lesson with electronic transitions that electrons can jump from lower energy orbits in Bohr's model to higher energy orbits. What that really means is they can jump from lower energy orbitals to higher energy orbitals if they receive a photon of light, if they absorb a photon of light of just the right amount of energy. And so in this case, iron normally looks like argon 4s2 3d6. But one of our 4s electrons has jumped up to something higher, a 5p. It's not where it would normally be. This is not the ground state electron configuration. This totally violates the Aufbau principle. But it wouldn't be a ground state, it would be an excited state. And so the last kind of question you might get is just identifying a possible excited state. Notice this is not the only excited state. I just had to have one of the normal electrons for iron anywhere higher. I made it 5p1. I could have made it 7p1 or, 6d or, I could have just chose one of these electrons to end up anywhere higher, and that would be an example of an excited state. Cool, and that's the last thing you might see as far as electron configurations go. So if you recall, we went through standard and noble gas configurations. We then moved on to the 5 exceptions: chromium, molybdenum, copper, silver, gold. We then talked about ions, both cations and anions, and the special case when you've got transition metal cations, and what you got to remember about pulling like 4s's before you remove 3ds. We then moved on to talk about the number of valence electrons, and then finally we dealt with the excited state in contrast to the ground state, which we've got all the rules for. But hopefully now you're in a position to do tons and tons of practice, because it does take a little bit of time to get down, but hopefully you've got a good foundation for doing so now. Now, if you found this lesson helpful, please consider giving me a like and a share. A couple of the best things you can do to help support the channel. And if you're looking for the study guide that goes with this, or if you are looking for practice quizzes and stuff like that online, check out my premium high school course on chadsprep.com.